Okay, now that we have been able to just construct our very first Bayesian regression model, now before just we add some spices into the arguments that we had inside the model, StanGLM, I'm just going to talk about a very important and crucial concepts in the Bayesian statistics, which philosophically it gives it a kind of a flavor different than the one which we had in the non-Bayesian or frequentist approach, which is going to be the discussion about, I should say, the credible interval. The credible intervals, or sometimes as we just named it, as it's going to be more relevant to, I should say, to the philosophy which is behind it, we just call that uncertainty interval. Then after that, we jump into our environment to just implement these concepts which you learn right now to some coding and just some tangible interpretation of these new concepts. The thing that we have learned so far in the past was that when we talked about, I should say, the statistical inference, this is going to be a very general definition of the statistical inference. It doesn't matter if you are from the frequentist approach or from the Bayesian approach. Normally, the thing that you have, it essentially falls into two different, I should say, definition. One of them is going to be a kind of a point estimate. Then essentially you try to get your best estimates, for example, of the mean of the population that you are studying. And also, the second thing which falls below, I should say, the statistical inference is the hypothesis testing. Which is not going to be the discussion that we are just going to make today. We are just going to talk today about something completely different, which is going to be the discussion about the point estimates. And that's how we are just going to come here to talk about, I should say, the credible intervals. The credible intervals, it's the definition which comes from the point estimates that you are just making in your Bayesian framework when you just come with an inference situation. And it seems that, for example, imagine that, for example, in the cases that we have about, for example, the American women datasets that we have, the thing that we were trying to just come with was that we were trying to find this model. We were trying to say that, for example, the height of these women, we assume that it's going to be a normal distribution which comes with the parameters inside the normal distribution, which is going to be a kind of a population mean, and also standard deviation, which is the kind of a measure for the dispersion from the mean population that we had. I mean this value, which we call that sigma. We saw that for this example that we were following so far, which it was an example that we had only one single variable embedded into our problem, we said that the mean population, we can say that we call that as a parameter, and that was the reason that we called the model that we were dealing with a parametric Bayesian inference. We said that the population knew that we were going to deal with it. It's going to follow this simple linear model, ax plus b, which we essentially call that, for example, the x which we have here, it can be interpreted as, let's say, as, for example, the weight of these American women. And essentially our inference problem was somehow reduced to this method, that we say that, for example, the mean of the height, it's going to be modeled as A, as, let's say, for example, the mean of the weights, plus an intercept B. that we were trying to find, I should say, the inferences about, let's say, we were trying to find the inferences about the A, which it was our slope, and also our intercept. However, when we are dealing with these kind of situations, when we find that, look at these parameters that we have here. We can call that also, for example, these parameters A and B that we have here. We say that if we come in our model, we say that, for example, imagine that the inference that we had, for example, it was our best estimates because we choose our algorithm to be, let's say, for example, we choose our algorithm in the running codes that we had. Our algorithm was supposed to be a sampling, which was essentially an MCMC methods, a dynamic Hamiltonian Monte Carlo. Then we say that for example, for the slope that we had, for example, in our case, we had a number which it was, for example, imagine it was 0.3. And for the B, we had, for example, almost 25.7. These were the values that we made an inference about them, somehow similar to the discussion that we had as a point estimates. And now the question is that with the estimates that we had in our methods, sometimes we say, okay, we come to say that sometimes we are not sure, we do not know exactly that, for example, if the 0.3 is going to be the true value of, let's say, of the slope in a modeling that we try to model the height with respect to the weight. We always attach a kind of an element, which we call that element, we call that uncertainty, to our inference, which as a result, when you add this uncertainty to the best estimates that you had, then you come here to represent the value of the A, which you say that it's going to belong to an interval. The interval, I'm just going to call the upper and the lower bound of that interval as, let's say, for example, alpha and beta. We say that the slope or the parameter that we were trying to run the model to just make our best estimates as our statistical inference of the problem that we had, we say that we do not want to say that it's going to be exactly 0.3. We have some elements of the uncertainty, then because of that we just come to an interval. We say that, okay, the A, it belongs to an interval with the lower bound of the alpha and the upper bound of the beta, and we say that the parameter A, it belongs to this interval, which this interval also belongs, I should say, to the posterior probability that you have in, I should say, in your model. Then that's essentially what we call that as credible interval. That's essentially what we call that the credible interval, because we assign for A probability that it should fall within a range. If you imagine that, for example, it's going to be, for example, that's going to be the value of, for example, of our parameter, which I call that the x bar, for example, here. And I have alpha here, and I have beta here. And I know that the A has to just fall in this interval, which is going to be from A to B, alpha to beta. Then you see that if you can narrow this interval from the alpha to beta, then if you can narrow this interval, you have a higher certainty that what's going to be the value for your parameter that you try to just have an inference about. The more wider the interval you have, the more uncertain that you become. That's going to be the true value of, I should say, the parameter that you are just making an inference. Then, based on the things that we learned, and as we're just getting close to the final, I should say, slides that I'm just going to wrap up, I should say, this discussion about the credible interval, then as a conclusion, we say that the parameters that we were trying to find, for example, in terms of, for example, the height, to be modeled as, let's say, for example, A times weight plus B, we say that when we just make an inference about the A, we are not sure that A is the true value of the parameter that we are just looking for. In the Bayesian approach, you assign A to an interval alpha and beta, and you assign a probability that the unseen parameter, that's the thing that I have to just emphasize on that the unseen parameter, alpha, falls within that interval. Then you come to say that, okay, in the Bayesian inference that you say that, for example, I am 80%, there is an 80%, you say that there is a probability, I'm just going to write it like that there is a probability that the true value of the parameter falls within the interval, or it can be an open interval, alpha and beta. That's essentially, that's the credible interval. We can, when we talked about the probability here, you can come with the probability and say that, for example, the probability that we were talking about, for example, this probability can be, for example, based on the codes that we have, for example, 90%. Probability, there is a 90% probability that the true value of the slope that you're looking for falls within the range. And now, as a very final point that we're just going to make the conclusion about that, is the discussion about the concepts that we learned about the credible intervals or uncertainty intervals versus the confidence interval, which is a kind of a concept in the non-Bayesian framework. But the thing that we discussed about the credible intervals, we saw that in the credible intervals, the parameter that you just want to make an inference is random. However, the interval is fixed. What do I mean? For example, the thing that we discussed was that, for example, about the slope, we said that the unseen slope, before, let's say, before we just run an experiment actually, and we found the slope, we assumed that the slope is gonna fall within an interval, which we call that interval alpha and beta, and we said that this unseen interval is gonna fall within this interval. We said then we see that the A, our slope, is going to be random. It can take any values within this range. But there is a probability assigned to it. However, when we come to talk about, I should say, the confidence interval, with the concepts of the confidence interval, the things is going to be a little bit different philosophically. We said that in the confidence interval, which is the framework of the non-Bayesian or frequentist approach, we said that the parameter that we are trying to make an inference, the parameter now is not random anymore. It's going to be fixed. However, the interval is going to be a random interval. This is essentially a kind of a comparisons of what is the credible intervals, which comes within the Bayesian framework, and the confidence interval, which is non-Bayesian framework or the frequentist system. Then we say that when we are talking about that thing, about the confidence interval also, we say that, okay, we know that when you go over that concept, you're going to see that clearly that, for example, the slope that you have just made an inference, you say that I know that the intercepts, it's going to be, for example, the slope, which I'm trying to make an inference, is going to be also belonging to this interval alpha and beta, but in the sense that you are trying to not find the probability of having the alpha within the range, you're capturing the probability for, I should say, for the upper and the lower intervals of your, I should say, the confidence interval that you are dealing with. Now, I think that's pretty much about, I should say, the thing that we needed to know about the credible intervals and the confidence intervals. On the tutorials that we run on the R, I should say, environment, we try to first of all deal with the credible intervals and also compare that with the confidence intervals that we discuss about it right now.